Hello everyone. Good evening to all. Guys, hi, all of you. So I'm launching the technical polls. Just respond to the polls whether my voice is clearly audible or not, and also my screen is visible clearly. Yes. Everyone, please respond to the polls whether my voice is clearly audible to you or not, and also my voice and my screen is visible clearly or not. Can you please respond to the polls, everyone, please? Okay. Okay, I think everything is good. So let's start your class today. We're going to continue the topic or chapter that is complex number, lecture 4. Okay, so we'll continue in these sessions. What we are going to cover in these sessions? First, we'll study complex number as vector. First thing is complex number as a vector. Already I told you before, also in the previous classes, complex number always behaves like a vector also. Right? So we'll study these things, complex number as a vector. Then we'll study cube root of unity. Okay, so these two things we'll try to cover in this session. Okay, so let's start with complex number as a vector. Okay, so let's start with that only. Okay, suppose we can say, suppose we have a point, right? If you have a point z, that is x plus iy, or if you have a complex number x plus yi, and you know we can represent a complex number in the organ plane as a point also. You know it or not? Yes, we know it. So we can represent it as also a point in the organ plane, which is x plus iy, and we can say it is also a complex number. So now I am talking about, can we represent it as a vector? Vector means will represent the complex number by the position vector. Is it possible? Yes or no? Yes. So point is P. Then we can represent this complex number as a position vector of P, point P, that is x plus iy. Or we can say no, it is represented by a vector, na? That is, we can represent it as a xi cap plus y j cap. You can understand now also. If you draw the figure, suppose this is my organ plane and this point is my P, whose coordinates are x, y. Okay. So if you draw a perpendicular from this point, okay, in vector we know, to reach this point, we need to cover x unit in x-axis, and also we need to move on y-axis y units to reach the point P. Is it or not? So similarly, here also, if you'll draw two perpendiculars from point P to real axis and also on the imaginary axis. Okay, so this is my point P, whose coordinate as xy, and also we can represent that is as z is equal to x plus iy. Okay, so what is position vector? If you join these 2 points, if you join, position vector means position vector of a point. That means the point from the origin, the line from the, or the vector from the origin. Yes or no? So this position vector OP, or we can write this as OP also. OP is actually xi cap plus y j cap. Yes or no? So complex number is like behaving like a vector here. Acha. So how can we know this is a vector or not? So we know by the definition of vector, a vector has magnitude as well as direction. Yes or no? vector as magnitude as well as direction. So already we have the direction, that is in the direction of the point P from the point O. So this is the direction. What is the magnitude? So magnitude is actually, if Z is equal to x plus y, then modulus of Z is under root of x square plus y square, right? And if P is x y cap, P is x I cap plus y j cap, then we can find the magnitude of point vector P. What is the magnitude of vector P? Is under root of x square plus y square. So you can observe here, what we are talking about, the complex number. Then similar things we are talking about the vector also, position vector of point P. Yes or no? Clear everyone? Guys, everything is clear or not? So from here we can conclude that so complex number behaves like a position vector of a point, and it is also a point in the organ plane also. Clear? So let's move to the another. Okay. Now distance between 2 points. If we'll discuss about the distance between 2 points in organ plane. And suppose we have, this is my organ plane and this is my vector PQ. Okay, and P has the coordinate x1, y1, and Q has the coordinate x2, y2, right? Then, and this can be represented as also Z1. I'm taking this complex number as Z1, and this is as Z2. Now, if I'll ask you to find the distance between two complex numbers, or distance between these 2 points PQ, or we can say distance between these two complex numbers. So what will happen? What should be the answer? So PQ will be, we can say, x2 minus x1 square plus y2 minus y1 square. Yes or no? Yeah. So what is the position vector of point P? What is the position vector of point P? That is x1 I cap plus y1 j cap. And what is the position vector of point Q? That is small q, that is x2 I cap plus y2 j cap. This one. Now, what is the vector PQ? What is the vector PQ? That is x2 minus x1 I cap plus y2 minus y1 j cap. All of these things we have studied in vector also, and now we are studying in complex number, right? So now if I'll ask you to find the magnitude of the vector PQ. Find magnitude of the vector PQ. So it will be same as x2 minus x1 square plus y2 minus y1 square. So position vector of point P is Z1. And we can represent it also. Position vector of point P is equal to Z1, which is x1 I cap plus y1. Sorry. We can represent now complex number. We can represent the position vector of point P as a complex number. Now that is also we can represent as x1 plus I y. And similarly, we can represent position vector of point Q, that is Z2, which is equal to x2 plus I y2. Yes or no? So now we can say that is the vector PQ is Z2 minus Z1. which is equal to x2 minus x1 I cap plus y2 minus y1 j cap. And the magnitude of point vector PQ is on root of x2 minus x1 whole square plus y2 minus y1. So see here what we are getting here actually. The thing is, what are the operations we are doing with the complex number? What is the things you are getting? Similarly, similar things you are getting when you are taking complex number as a position vector. Yes or no? Everybody, can you respond to the chat box? Is it clear to all? Yeah. Clear? Okay. Now, this is all about your complex number as a vector. Okay. And now we'll study triangle inequality. So what is triangle inequality? All of you know, if you have a triangle here, suppose this is my triangle. Okay. And this point is A, this point is B, this point is C. And suppose this is my side B, this is my side B. This is my side A and this is my side C, small c. Okay. So we know from the law of triangle law, that is sum of two sides A plus B is greater than the third side. Sum of two sides is greater than the third side and difference of two sides is less than the third side. So these things we know about triangle. Yes or no? All of you know that things. Yes or no? So by using these principles, we can develop the triangle inequality in complex number also. What are those? Let's start. Okay, so first law is saying mod of Z1 minus mod of Z2 is less than equal to mod of Z1 plus Z2, which is less than equal to also Z1 mod of Z1 plus mod of Z2. Is that clear to all of you or not? You can draw a figure also. Suppose this is my organ plane and this point is P. I'm taking this point is P, which is also Z1. And this point is Q, complex number Z2 also. Right? So if we'll take the position vector of point P, this will be the position of a point P. And if we'll take the position vector of point Q, this, and now if I'll ask to find Z1 plus Z2, so then Z1 plus Z2 will be, what will be Z1 plus Z2? That is actually, if we'll add these two complex numbers, where it will be lying? Suppose this point, that is R. Suppose I'm taking Z1 plus Z2. Now if we'll join these points, now you can see here, if we'll join from origin to the point R, now see, OR length, that is mod of Z1 plus Z2 or not. Now you can observe first triangle inequality will be satisfying, that is mod of Z1 plus Z2 is less than mod of Z1 plus mod of Z2. So this is if we'll take the triangle OPR. If we'll take the triangle OPR, you can observe sum of two sides is greater than actually the third side. So what is the third side here? OR. And what is the sum of two sides? That is OP plus OR is greater than OR. OP plus PR is greater than OR. Second thing, what you are getting? second thing I am getting here, that is mod of Z1 minus mod of Z2 is less than mod of Z1 plus Z2 by using this principle. Yes or no? So these are two inequalities we are getting, right? Similarly, also remember this is the very important triangle inequality you can observe from this figure also, right? So now we'll go through the second inequality, that is, just I am telling you the inequality, that is mod of Z1 minus Z2 is less than equal to mod of Z1 minus Z2 is less than equal to mod of Z1 plus mod of Z2. Okay, so this is the second inequality of triangle inequality. Okay, clear? You can observe from the second figure here. From this triangle, red shaded triangle, you can observe here. Okay. Okay, so this is all about the triangle inequality. Now we'll go through the rotation theorem. So what is rotation theorem says? Okay, suppose you have a complex number Z1 and which Euler's form is R into e to the power I alpha. Okay, so can we represent it in the organ plane? Yes, we can represent because we have the argument also. Suppose we have a circle here, this, right? And Z1, suppose this is the point Z1. This point is Z1. So that means argument of Z1 is alpha. So this angle is alpha. Yes, and the radius is R. Okay. Now if we'll take another point Z2. Okay. So which is R is equal R into e to the power I into alpha plus theta. R into e to the power I alpha plus theta. Then alpha plus theta means we need to take an angle from, we need to make an angle, or we need to take a point, that is Q also. I'm taking, suppose this point Q, and which is represented at the complex number Z2. So then this angle will be theta. This angle will be theta. Then the argument of Z2 is R plus theta. Yes or no? So this can be also written as R into e to the power I alpha plus I theta. Yes or no? Yes. So this can be also written as e to the power I alpha into e to the power I theta also. So what you are getting here? What you are getting here? So we know, we already have taken Z1 is equal to R into e to the power I alpha. So this is my Z1 or not? Yes. So we can write this as Z1 into e to the power I. Z1 into e to the power I theta. So the conclusion is, when we are multiplying e to the power I theta, e to the power I of any angle with any complex number, then the complex number moves that theta angle from the complex number, from the previous complex number. Like here, we already have a complex number Z1. If you are multiplying with e to the power I theta, if you are multiplying e to the power I theta, then this complex number Z1 rotate theta angle from the complex number Z1 to Z2. Is it or not? That's why its name is called rotation theorem. So the conclusion, what is the conclusion of rotation theorem? Now, when we are multiplying e to the power I theta with a complex number, okay, then what is happening? Now that complex number rotate theta angle, or that complex number rotate theta angles from Z1. Z1 rotates theta angles in anticlockwise directions also. We can say here in we are discussing about the anticlockwise direction. Yes or no? Clear? So then move to the okay. If we'll study, if you can ask, sir, what if we'll rotate it in clockwise direction? What is that? So let's see. Clockwise and anti-clockwise rotation. Okay, clockwise and anti-clockwise rotation. So suppose we have a circle here, and this is my organ plane. This is my organ plane. Now I'm taking a point P here. P. Okay, I'm taking OQ and also a point Q. Okay, if you'll join OP and OQ. See here. That is, we can say OQ vector is equal to OQ vector is equal to OP vector into e to the power I theta. Or also you can, if you'll take Z1, this is Z2, then Z2 vector is equal to Z1 into e to the power I theta, if this angle is theta. Yes or no? Similarly, conversely, we can say OP vector is equal to OQ vector into e to the power minus I theta. If we'll rotate in clockwise direction, if we'll rotate in clockwise direction, that means this is my anti-clockwise direction, this is my clockwise direction. So when we are measuring the angle in clockwise direction, that angle becomes negative. Yes or no? So OP is equal to OQ into e to the power I theta. Also we can say Z1 is equal to Z2 into e to the power minus I theta also. So this is all about your clockwise and anti-clockwise rotation. Right? Is that clear to everyone, guys? Clear? Yes or no? Clear, everyone? Sure. So this is all about your, what is that? Rotation theorem. Just a minute. Sure. Now we start the next thing, that is de Moivre's theorem. Very important theorem. De Moivre's theorem. Okay. So what is de Moivre's theorem? Its statement is, I'm talking about the first case. Case 1 I'm taking first. Statement is, if n is any integer, if n is any integer, then cos of theta plus I sine of theta whole to the power n can be expressed as cos of n theta plus I sine of n theta. Okay. Chalega? Do you need the proof? Okay, let's see what is the proof. So proof is, see, if you'll take the left hand side, that is cos of theta plus I sine of theta whole to the power n, then this in inner expression can be expressed as e to the power I theta whole to the power n. Yes or no? Can we write this as e to the power I into n theta? Yes, we can write. So by using the Euler's identity, we can express this e to the power I into n theta as cos of n theta plus I into sine of n theta. Is there any doubt? No. So now it is proved or not? Now it is proved or not? So first case is proved. Second, in generally we can say second thing is cos of theta 1 plus cos of theta 1 plus I sine of theta 1 into cos of theta 2 plus I sine of theta 2 into cos of theta 3 plus I sine of theta 3 and so on up to cos of theta n plus I sine of theta n. That can be expressed as also cos of theta 1 plus theta 2 plus theta 3 up to plus theta n plus I sine of theta 1 plus theta 2 plus theta 3 up to theta n. Okay, clear? So what is the proof? You need the proof. Okay, let's see what is the proof. So proof is very simple. If we take the left hand side, so this expression can be written as e to the power I theta 1 and this expression can be written as e to the power I theta 2. This expression can be written as e to the power I theta 3 into up to so on e to the power I theta n. So if you multiply all these exponential terms, what will be you are getting e to the power I theta 1 plus theta 2 plus theta 3 up to plus theta n. Okay, if you use the Euler's identity, क्या हो जाएगा बेटा? Now this will be cos of theta 1 plus theta 2 plus theta 3 up to theta n plus I into sine of theta 1 plus theta 2 up to theta n. Yes or no? So this is my left hand side. Okay, is that or not? This is my left hand side. Now it is proved, everyone. Now it is proved or not? Yes, it is proved. Okay, so this is all about your case 1. So what is case 1? Sorry, case 1 when this is my case 1 and this is my case 2 and it is also proved. Clear? So both the statement of case 1 is proved. Now we'll go through the case 2. What is case 2? Case 2 is saying this is all about a de Moivre's theorem. Okay, if just a minute. If statement is if PQ belongs to the set of complex number or integers. Okay, sorry. If PQ are two integers and Q is not equal to 0, then we can say cos of theta plus I sine of theta to the power P by Q is equal to cos of 2k pi plus P theta upon Q plus I sine of 2k pi plus P theta upon Q, where k belongs to k is equal to 0, 1, 2, 3 up to Q minus 1. Okay, so this is the second case of de Moivre's theorem. Do you need the proof of this, guys? Okay, so we'll go through the proof first. So let's see what is the proof of this theorem. So we have in the left hand side, that is cos of theta plus I sine of theta whole to the power p by q. It can be also written as cos of theta plus I sine of theta to the power p whole to the power 1 by q. Yes or no? You can write or not? Yes. So by using the de Moivre's theorem, we can write this as also in the interior expressions. If we use the de Moivre's theorem, so what will happen? This becomes cos of p theta plus I sine of p theta whole to the power 1 by q or not? Yeah. So also, can I write cos of p theta as cos of 2k pi plus p theta? Yes, I can write or not? Yes. Similarly, I sine of 2k pi plus p theta we can write. Yeah, no issues, because trigonometric functions are periodic functions. So in place of p theta, if you write 2k pi plus p theta, this will gives again you cos of p theta. Similarly, in place of cos of p theta, if you write sine of p theta, if you write sine of 2k pi plus p theta, also it gives you sine of p theta. Right? So now, by using the de Moivre's theorem again here, what you are getting? That is cos of 2k pi plus p theta upon q plus I into sine of 2k pi plus p theta upon q. Yes or no? So now it is proved. Yes, is it clear to all? Clear? ठीक है ना? Okay, okay. So, कोई नहीं. Now we'll move through. This is all about your de Moivre's theorem. This is case 2, and this is your case second portion of case 1. This is the first portion. Now we'll study about the very much interesting topic, that is cube root of unity. So unity means one. Na? We are not talking about unit. We are talking about unity. So that is unity means one. So cube root of unity. First we'll use the first method. Let's understand the first method to find the cube root of unity. Okay. Suppose you have equations like z is equal to z cube is equal to 1. Then it's a cube root of unity. Okay, let's talking about like this. Z is equal to 1 to the power 1 by 3. Now we can say z cube is equal to 1. Listen, if we'll take the cube on both sides, so we'll get z cube is equal to 1. So then we are getting the equation z cube minus 1 is equal to 0. Listen. So this is a cubic equation. This is a cubic equation. Okay. So if this is a cubic equations, that means this equation has 3 roots. Okay. So can you tell me what are those roots? Can you tell me what are those roots? If there are 3 roots, then what are those? Okay. So you can say easily one root is z is equal to 1. Yes. 1 is a root of this equation. Correct. Very good. So if 1 is a root, we can use a factorization method also. So z minus 1 into z square plus z plus 1. We can write, you can factorize this z cube minus 1 as z minus 1 into z square plus z plus 1 is which is equal to 0. So we are getting here, or you can use the aq minus bq formula also here. And you can get z is equal to 1, or you can use the heat and trial method. That is z is equal to 1 is the root, then we can factorize this z minus 1 into z square plus z plus 1 is equal to 0. So one root we are getting, that is z is equal to 1. Okay. Or another, from these equations we are getting z minus 1 is equal to 0, or z square plus z plus 1 is equal to 0. So from by solving this equal to 0, we are getting z is equal to 1. So when we are solving z square plus z plus 1 is equal to 0, what we are getting? Use the discriminant method. Use the discriminant method. What are the roots you are getting? Already we solved these equations previously also. Okay. So by solving this one, we are getting z is equal to minus b plus or minus on root of b square minus 4 into 1 into c, that is minus 4 upon 2a. Right. So here we are getting minus 1 plus or minus root 3i upon 2. So two roots we are getting. One is minus 1 plus root 3i upon 2, and minus 1 minus root 3i upon 2. So one is, so first root is z is equal to 1, second root is minus 1 plus root 3i upon 2, and third root is minus 1 upon minus 1 minus root 3i upon 2. This is my third root. This is my second root. This is my first root, and this is my third root. So we are now we got the three roots of the cubic equation z cube minus 1 is equal to 0. So this is the first method to find the cube root of unity. Okay. So this is the first method to find the cube root of unity. So now we are discussing about another method, that is, what is the second method? Now we'll use the de Moivre's theorem to find the root of the cube root of unity. So method 2. What is the second method? Now second method is, see, if z is equal to 1 to the power 1 by 3, so we can express this as z is equal to, use the de Moivre's theorem, second case of de Moivre's theorem, this case. If you use this case, what you will get? Z is equal to 1 to the power 1 by 3. So we can express 1 in the polar form also. That is cos of 0 plus I sine of 0 whole to the power 1 by 3. And we know since z is equal to cos of theta plus I sine of theta whole to the power p by q. We know this formula. Using this one, we can say z is equal to 1 can be expressed as cos 0 plus I sine 0 whole to the power 1 by 3. Now if we use the de Moivre, second case of de Moivre's theorem, so what we will get? So cos of 2k pi plus 0, 2k pi plus 0, theta, not I'm taking theta here, theta is 0 upon 3, that is q. P is 0 na. This is p, this is p. P is 0. 2k pi plus p by q plus I sine into 2k pi plus 0 upon 3. Okay. So if you put k is equal to 1, 2, 3. So first put k is equal to 1 in this expression. Put k is equal to 1. What you are getting? When you are putting k is equal to 1, we are getting z is equal to 1 also. Because k is equal to cos 2 pi. Cos 2 pi by 3 will be 0. And sine 2 pi by 3 will be 1. Right? So this becomes z is equal to 1. If you are getting, sorry, 0, 1, 2, na? Sorry, 0, 1, 2. We put 0, 1, 2. So first we are taking cos k is equal to 0. Then cos 0 will be 1 and sine 0 will be 0. So z is equal to 1. By putting k is equal to 0, we are getting z is equal to 1. So if we put k is equal to 1, in the above equation. Okay, try to put k is equal to 1. So we are getting cos of 2 pi by 3 plus I sine of 2 pi by 3. So what is the solutions you are getting? Cos of 2 pi by 3 is minus 1 by 2 plus this sine I into sine of 2 pi by 3. Sine of 2 pi by 3 is root 3 by 2 I. Okay. And if we'll put k is equal to 2, we are getting cos of 4 pi by 3 plus I sine of 4 pi by 3. Yes. So this gives you minus 1 by 2 minus root 3 by 2I. Clear? Yes or no? Tell me. Now you got the first root by using the de Moivre, you will get the first root, second root, and the third root. Okay. Clear not? Clear or not? Right? So similarly, we can use the Euler's form use करके भी तुम बता सकते हो, ठीक है? You can use the Euler's form also. You can find the all the roots, right? What is the Euler's theorem? By using the Euler's theorem. Suppose second method, I am taking z is equal to 1 to the power 1 by 3. So this can be expressed as cos 0 plus I sine 0 to the power 1 by 3. Also we can write this as cos of 2k pi by 3 plus I sine of 2k pi by 3. Yes or no? By using the de Moivre's theorem. Now, by using the Euler's identity also, we can write this as I into e to the power I into 2k pi by 3. Now, if we put k is equal to 0, 1, 2. Then also, at k is equal to 0, you will get z is equal to 1. And k is equal to 1, you will get z is equal to same minus 1 by 2 plus root 3 by 2 I. And k is equal to 2 के लिए, for k is equal to 2, you will get z is equal to minus 1 by 2 minus root 3 by 2. So these are the three roots you will get. Okay. So notation is, now we'll summarize all these things. Okay. If we'll summarize all these things, what are the things you are getting? Cube root of unity. If we'll summarize all these things. So what are the Cartesian form? Cartesian form of cube root of unity, 1, that is minus 1 by 2 plus root 3 by 2 I. Third one is minus 1 by 2 minus root 3 by 2. Okay. Now we'll talking about the polar form. Polar form is, one is 1, second is cos of 2 pi by 3 plus I sine of 2 pi by 3. And third one is cos of 4 pi by 3 plus I sine of 4 pi by 3. If we're talking about the Euler's form is, tell me, first is 1, second is e to the power I 2 pi by 3 and e to the power I 4 pi by 3. And this is about Euler's form. Now we'll give the notation. What are the notation of cube root of unity? 1, we'll use 1 as 1. If we'll take this as omega, if we'll take this root as omega, then the second one will be omega square. Okay. And also, if we'll take this as 1, this as omega, then this can be written as omega bar or conjugate of omega, because this is this root is conjugate of this. Yes or no? So then, if this is omega, this will be omega bar or conjugate of omega. So these are the notation of complex cube root of unity. that clear to everyone? Guys, is that clear to everyone? Everyone? Okay. Now we'll study some properties about cube root of unity. Property. First property is saying cube root of unity are in GP. Yes, why not? Because 1 omega square. So what are the common ratio here? If we multiply 1 with omega, we are getting second. If we multiply omega with omega, then we are getting the third one. Then they are in GP. Yes or no? What is the second property? Sum of roots is 0. And the sum of roots is 0. That is 1 plus omega square is equal to G. Yes or no? Yes or no? 1 plus omega square is equal to 0. The sum of roots is 0. Okay, you can use the sum of roots wala formula also, right? And also we know na 1 plus z square plus z plus 1 is equal to 0. If omega is the root of this equation, if omega, we know na z square plus z1 is equal, z plus 1 is equal to 0. If omega is the root of this equation, then this equation will be true. That is 1 plus omega square is equal to 0. In general, we can say 1 to the power r plus omega to the power r plus omega to the power 2r also equal to 0 when r belongs to the set of integer. But it is not a multiple of 3. Right? Multiple of 3. Okay. If it is a multiple of 3, when r is not a multiple of 3, 1 to the power r plus omega to the power r plus omega to the power 2r gives you 0. If r is a multiple of 3, what will happen? Then if r is a multiple of 3, then it will happen 1 to the power r plus omega to the power r plus omega to the power 2r gives you 3. When r is a multiple of 3. Clear? Clear, everyone? Okay. Let's solve one question. Example I am taking first. So 1 square plus, I am taking the some r as any integer which is not a multiple of 3. Omega square plus omega square ka square. So what we are getting? 1 square plus omega square is omega square plus omega to the power 4. Right? So we can write this as 1 plus omega square plus omega to the power 4 can be written as omega cube into omega. And we know z cube is equal to z cube minus 1 is equal to 0. And omega is the root of this equation. Then omega cube is equal to 1. Right? So omega cube becomes 1. So 1 plus omega square is equal to 0 or not. So when r is, already we know na, 1 plus omega square is equal to 0. So when r is not a multiple of 3, then the sum of 1 to the power r plus omega to the power r plus omega square to the power r gives you 0. Right? Okay. Now, if it is a multiple of 3, then verify it is giving you 3 or not. Okay. So let's verify that also. Second thing, if we'll take 1 to the power q plus omega to the power q plus omega square to the power q. Then see, this becomes 1 plus omega q plus omega to the power 6. Okay. So we can write this as 1 plus omega cube plus omega cube to the power 2. So here 1 plus omega cube is 1 plus omega cube is 1 square. That is also 3. Right? So when we are taking R is a multiple of 3, then we can say it gives this sum gives you 3. Clear? Clear, everyone? Okay. Now come to the third property. What is the third property here? The product of roots is 1. Product of cube root of unity is 1. That's very bad. That means 1 into omega square, which is equal to omega cube. This is equal to 1. Yes or no? Clear? Yes or no? Okay. If this is true, sure. If this is also true, now try to solve one question here. I'm giving you one question. Question is, if omega is not equal to 1, is a cube root of unity, and 1 plus omega to the power 7 is equal to a plus b omega, then find the value of a and b. So I'm giving you, for these questions, I'm giving you 1 minute. And your time starts now. Try to solve it. Okay. So it's time. Anyone got the answer? Can you please respond in the chat box who got the answer? Let's see what is the solution. So it is given that omega, which is not equal to 1, and it's a cube root of unity, and 1 plus omega to the power 7 is given as a plus b omega. So we know 1 plus omega square is equal to 0. Then can we say 1 plus omega is equal to minus omega square? Yes. So by using this, we can write this as minus omega square to the power 7. Achha. So we can write this as minus omega to the power 14. Yes or no? Okay. Now, if we'll try to write this as minus omega to the power 12 into omega square, is there any problem? No. Right? So this becomes, and omega to the power 12 can be written as omega to the power 3 or to the power 4. So when in the power we are getting the multiple of 3, then this becomes 1, right? So omega square. So this becomes 1 and minus omega square. So this is equal to minus omega square. So minus omega square is also written as 1 plus omega square. So 1 plus omega square is equal to a plus b omega. Okay. So what are the values of a and b we are getting here? So a becomes 1 and b is also, yes or no? A becomes 1 and also b becomes 1. Omega square is equal to 1 plus omega, no? Sorry. So 1 plus omega you are getting. So 1 plus omega is equal to a plus b omega. If you'll compare both sides, we are getting a is equal to 1 and also b is equal to 1. Yes or no? Is it true or not? Clear? Okay, now I'm giving you one homework question also. First question is, let omega is equal to minus 1 by 2 plus root 3 by 2 I. Then find the value of this determinant. 1, 1, 1, 1 minus 1 minus omega square, 1 omega square, omega to the power 4. I'm giving you also is options are given. First is 3 omega, second is 3 omega into omega minus 1, third is 3 omega square, and last one is 3 omega into 1 minus omega. Okay, so can you please note down the questions for the homework questions? This is the question for your homework. And write the second questions also. Second question is, if I is equal to on root of -1, then 4 plus 5 into minus 1 by 2 plus root 3 by 2 I whole to the power 334 plus 3 into minus 1 by 2 plus root 3 by 2 I whole to the power 365. Okay, so then find this is. Answers are, first one is 1 minus I root 3, second is minus 1 plus I root 3, third is I root 3, and last one is minus I root 3. So these are two homework questions for you. This is my second question given as your homework questions, and this is your first question. It's also take as your homework. You can note down these two questions also, and you can solve to the next class. Okay, and my suggestion is, it's already completed. 95% of the concepts are completed, but 5% were left with. But the important portions are completed here. Okay, and in this course, in these chapters, at least 2 questions will be coming in JEE mains, and in other examinations also you will get more questions. So take this chapter as seriously, and also solve a lot of questions from this topic. You can solve any modules also, you can solve any standard books also, and you will able to solve the questions those are coming in the competitive examinations, and board questions will be very easy and you can solve it. Okay, so till now we have completed the chapter that is complex number. From next week we'll try to start sequence and series. Okay, so that's all for today's class. Thank you all. Bye bye. Take care everyone.